In this video, I'm going to cover chapter 6 of my stochastic modeling book. That's the chapter about Galton-Watson branching processes. So those processes are general stochastic models that describe the dynamics of population and that can be studied using results from martingale theory. In particular, you can think of this video as an application of my previous video about martingales. More precisely, here are the different aspects of the model we are going to study. And as usual, if you are interested in a specific part of this video, check out the thumbnail or the description of the video with the table of contents and the different timings, so you can skip directly to the part you are interested in. So like the name suggests, Galton-Watson branching processes were introduced by Francis Galton here and Henry Watson. So first, I'm going to give you a rigorous definition of what we mean by Galton-Watson branching processes. We'll see that those processes describe the dynamics of a population, keeping track of the size of a population over time. And those processes are characterized by something that we call the offspring distribution. So the offspring distribution is basically a discrete random variable with values in the natural numbers that describe the random number of offspring per individual. The process also assumes some kind of homogeneity and independence across space and time in the sense that the offspring distribution attached to different individuals are independent and identically distributed. Okay? So I'm also going to briefly mention this notion of Galton-Watson tree. So a Galton-Watson branching process is a discrete time process that turns out to be a discrete time Markov chain. At the opposite, a Galton-Watson tree is a random graph. Okay? But it helps to have this idea of Galton-Watson tree in mind because that gives you some kind of visualization of the process itself. The process keeps track of number of individuals at each time step or at each generation. The Galton-Watson tree shows you some kind of connection among those individuals having some ages connecting parents and offspring, and it helps to think of a Galton-Watson branching process as in fact a Galton-Watson tree, which is some kind of visualization to better understand the process, and that's going to help also to prove results about Galton-Watson branching processes. So, like I told you, it turns out that this process is a discrete time Markov chain. We are going to prove that. That's not very difficult, but that's not the most useful to prove results about Galton-Watson branching processes. What's the most useful is the connection between the process and martingales. So it turns out that hidden behind a Galton-Watson branching process, there is a martingale. And once you identify this martingale, you can say a lot of things about the process. So first, I'm going to show you this connection, and we'll see that depending on the offspring distribution, the Galton-Watson branching process itself can be a super martingale, a martingale, or a sub-martingale. Okay? So now, because a super martingale tends to decrease on average, while a sub-martingale tends to increase, we are going to call this part, the set of offspring distribution such that the process is a super martingale. This is going to be called the subcritical phase. At the opposite, when we have a sub-martingale, we are going to call that the supercritical phase. And when the process is exactly a martingale, we are going to call that the critical phase. Okay? So now, in view of the terminology and the type of behavior that we expect from super martingale and sub-martingale, we expect that in the subcritical phase, we are going to have extinction of the population with probability 1, while in the supercritical phase, we are going to have survival of the population with a positive probability. Okay? And in the rest of this video, not only I'm going to indeed prove those results, but we are going to, in fact, prove much more. All right, so first, looking at the subcritical phase, it's extremely easy to prove that not only we have extinction of the process with probability 1, but also we have exponential decay. So that means that the population is going to die out exponentially fast, in the sense that the probability that the time to extinction is larger than some integer n is going to be less than a function of n that goes to 0 exponentially fast. All right, so that's the first aspect. This analysis of the subcritical phase is extremely easy. Now, a little bit more tricky is what happens in the critical phase, and this case is the most surprising, in fact. Okay, what's going on here is kind of weird, and so basically what we are going to do first is use the Martingale convergence theorem to prove that exactly like in the subcritical phase, we again have almost sure extinction of the population. Okay, but using the monotone convergence theorem, we can also study the expected number of individuals in the process. So by that I mean the total number of individuals in the process across space and time, okay, from time 0 to the time to extinction. Now, if we study the expected value of that total number of individuals, we can prove that this quantity is infinite. Okay, so eventually what we are going to prove is that in the critical phase, something a little bit weird and surprising happens. That's the fact that the total number of individuals across space and time in your process is almost surely finite with probability 1, but infinite on average. Okay? So that's what happens in the critical phase. The fact that the expected number, the expected value of the total number in the process is infinite implies that this extinction cannot happen like here, exponentially fast. Okay, so you may have a very slow extinction. Okay, in the critical phase. Then finally, we are going to look at the supercritical phase. So what happens in this case is what we expect. There is no surprise like here. What happens is that with positive probability, the population is going to survive forever. But the mathematics that we are going to use here is quite interesting, and we are going to basically see new tools that I didn't define before that can be used to study Galton-Watson branching processes in this supercritical phase. So first, the goal is to understand this quantity here. That's the probability of extinction of the process by time n. And so obviously, if we understand that well, that's going to give us some important information about the probability of survival. Right? So now it turns out that to understand this probability of extinction by time n, it's going to help a lot to study also what we call the probability generating function. And here, what I mean by that is probability generating function of the offspring distribution. It turns out that the two are related. And eventually, using this connection, we can prove that the probability of extinction of the process in the supercritical phase is going to be a fixed point of this probability generating function. Then after studying more carefully the probability generating function of the offspring distribution, in the case where the process is a sub-martingale, we'll be able to, in fact, have some kind of implicit expression for the probability of survival of the Galton-Watson branching process, and we'll be able to prove that this probability of survival is strictly positive, but also we'll have some kind of implicit expression, and we'll see that in some particular cases we can actually compute explicitly this probability of survival. So first I'm going to give you a precise definition of the notions of Galton-Watson branching process and Galton-Watson tree. So the assumption in the background for Galton-Watson branching process is the following. So you have something that evolves in discrete time, and we are going to assume that at each time step, individuals independently produce K offspring with the same probability Pk. So those probabilities Pk, they are the terms of a probability mass function. That's the probability mass function of this random variable that I call the offspring distribution. So this random variable describes the number of offspring per individual. And you see two keywords in the description, the word independent and the word same distribution, same probability. That means, and that's a very important assumption in this model, that means that if you look at different individuals in your process, then the random number of offspring produced by those individuals are going to be described by random variables that are independent and all have the same probability mass function or the same distribution given by probability that this random variable is equal to k is equal to pk. Okay, so these are the main assumptions of the model. Then the Galton-Watson branching process itself is going to be this discrete time stochastic process xn that keeps track of the number of individuals at time or generation n. We are going to assume to fix the IDs that x0 is equal to 1. Now, before we go to the next step, I want to comment a little bit on the distinction between those notions of time and generation. That doesn't really matter to do the math, to study the process, but that's important to understand this distinction so that you understand well the model. So, the word time is the word we use in the framework of stochastic processes, okay? This xn here is the state of the process at time n. We use the word time. Now, the two notions, time and generation, are going to match if you deal with a species with a non-overlapping generation. Okay, so that's a terminology from mass biology, non-overlapping generation. So an examples of species with non-overlapping generation would be annual plants, for instance, that all produce a bunch of seeds at about the same time of the year. All those seeds, they go in the soil and they form, they create what we call a seed bank. Then all those plants are going to die. And then at the next spring, all the seeds in the soil are going to germinate and create new individuals. You see that in this case, parent and offspring do not live at the same time. Individuals from two different generations are not going to live at the same time. In this case, the notion of time and generation are more or less the same. But if you think of a species with overlapping generation, like human being, for instance, where individuals from different generations typically can live at the same time, or at least their lifespan overlap, or at the opposite, you may have individuals from the same generation that do not live at the same time, then in this case, the notion of time and generation do not match. Okay? So, to really understand what is a Galton-Watson branching process, it helps to have in mind that, in fact, this integer n is not really interpreted as time, even if this is the word we use in the framework of stochastic processes. It's more interpreted as a generation. Okay? So that you understand the model well. But now, to do the mathematical analysis, we don't need to do this distinction. All right. So now from that, how can we have a rigorous definition of a Galton-Watson branching process? So one way to try to understand how we can construct mathematically a stochastic process would be to first try to simulate the process using a computer. If you can simulate a process using a computer, then that means that you probably have a very good understanding of the mathematical definition. So how would you simulate this process? Well, step one, you see that a key random variable in the story is something I'm going to call capital Y. That's a random variable that is equal to k with probability pk. We need to be able to generate that. We know what this means from a mathematical point of view, so we don't really need that for the mathematical analysis, but I can teach you one more thing and just tell you briefly how you can simulate using a computer any discrete random variable. So again, let's assume that y is the random variable equal to k with probability pk. How do you simulate that? What you do to simulate that, you take your interval 0, 1, and you take a subdivision of your interval 0, 1 into subintervals with lengths p0, p1, p2, p3, and so on. Okay? Because those pk add up to 1, they are the terms of a probability mass function, they, like your subdivision is indeed going to cover your interval 0, 1. That's indeed a subdivision of the interval 0, 1. Then you are going to generate a uniform random variable in the interval 0, 1. Okay, that's pretty much the only thing a computer knows how to do. Okay, and if your random variable, uniform random variable, falls in the interval of length pk, and notice that this indeed happens with probability pk, then you decide that your random variable y describing the number of offspring is going to be equal to k. Okay, that's how you generate using, or how you simulate using a computer a discrete random variable. All right, so that's step 1. Then step 2, you want to use this simulation program, this simulation of your random variable y multiple times to be able to decide how many offspring each individual is going to have, and you want to construct your process xn step by step, okay? And to understand how you do this, like the algorithm, it helps to have in mind the picture of a Galton-Watson tree, okay? So Galton-Watson tree is a random tree that can look like that. That's a rooted tree that starts with one vertex, and then you have a random number of edges going down like that, starting from each vertex, okay? So the way this tree is constructed is by using multiple independent outcomes of the same random variable y that is equal to k with probability pk, okay? So you generate your random variable y here, and let's say the outcome is 2. Then you are going to draw 2 edges like that. That's going to give you 2 vertices at generation 1. Then at this time, okay, second step in your program, you are going to generate 2 of those random variables y. Maybe let's say that the first one gives you the outcome 3 and the second one gives you the outcome 1. So you draw 3 edges here and 1 edge here that gives you 4 vertices, and you keep on going like that, okay? So the way this graph is simulated is again by having multiple simulations of the same random variable y, and in this case, the outcomes of your random variable y are given by those numbers, 2, 3, 1, 1, 2, 0, 2, and so on, okay? So if you get a 2, you draw 2 edges, if you get a 3, you draw 3 edges, and so on, okay? So now, how do you connect this feature and this process? Well, just think of each edge in this tree as connecting 2 vertices that are the parent at the top and the offspring at the bottom. Okay, that's exactly what it does. You just say, this first vertex is our first individual. Okay, and then this individual is going to produce 2 individuals, 2 offspring with probability P2. And so with probability P2, you have those 2 edges that gives you your 2 individuals at generation 1. And then you just say that, okay, now I have 2 individuals, so next step in the program, I'm going to simulate this random variable y twice in a row. Once to know how many offspring this individual is going to have, and another time to know how many offspring this individual is going to have. If you get 3 and 1, then that tells you that you have 4 vertices here. So 4 individuals at generation 2, and so on. That's how you can construct your process xn. Okay? then eventually you can see that from the tree, you can deduce that in this particular case, x0 equals 1, x1 equals 2, x2 equals 4, x3 equals 1, 2, 3, 4, 5, and so on. Okay? So that's by using a bunch of independent realization of the same random variable y that you can build this tree, and you see that indeed once you have the tree, you can find the value of those xn. Okay, so notice that in fact there is not a one-to-one correspondence between a realization of your process and a realization of the tree. The tree gives you more information. If you have the tree, you can just count the number of vertices at each level. That's going to give you the value of xn, like we did here. At the opposite, if you only know the process xn, you only know the number of vertices at each level, but you don't know where the edges are. And so that basically means that you don't know who gives birth to whom. Okay? So the tree gives you more information, but more or less, to generate the process, you kind of generate this tree here. Okay, so that was the algorithm you can follow to generate, to simulate a Galton-Watson branching process. Now, next step, how can we use that to actually construct the process mathematically? You see that when you build this tree using a computer, you first look at the outcome of the first random variable, that gives you a 2, then you are at this step only going to generate 2 more of those random variables, not more than that, because that's time consuming for the computer. You want your computer to go as fast as possible. In math, we don't care about time, about how much time it's going to take. We can just take infinitely many random variables at once. And that's basically what we are going to do. The way you construct your process mathematically is more or less by following this algorithm and constructing this tree, but you don't need to do it step by step. You can just take a bunch of random variables, infinitely many of them, that are going to describe the number of edges of any potential vertex in your graph. So more precisely, I'm just going to take a doubly infinite collection of random variables that I'm going to call y and I. So those y and I, they have the same distribution as this random variable y that I told you how to simulate. And all those y and I, they are independent, identically distributed, and equal to k with the same probability pk. This is defined for all n larger or equal to 0 and for all I strictly larger than 0. Then notice that, so what is this y and I in our picture, for instance? What is the interpretation of that? Well, that's going to be the number of offspring produced by individual I at time n. But notice I precise if this individual exists, okay? If you simulate your process, you want to do it as fast as possible. You don't want to ask your computer to do extra calculations that are useless. But in math, it doesn't matter. You just take infinitely many of those random variables and you only use the one you need. Okay? So for instance, going back to this picture, you would have, for instance, the first one, y01 is equal to 2. Okay? And then you can use y11 and y12 to see the number of offspring of those individuals. Then somewhere in the background, you also have y13, y14, and so on. They are here. We don't need to use them. Okay? But if this was 3 or 4, then we would need to use them. So to simplify things, instead of taking exactly what we need, like when you would write a simulation program, instead we just take a doubly infinite collection and we say, okay, we have everything we need, much more than what we need. It doesn't matter. In math, we can take infinitely many of those random variables at once. Okay? So that's how you would basically like construct the process, like having like all those, like generating all those numbers in the graph that are important to construct the process Xn. Now, what is exactly the process Xn? How can you use those random variables to actually construct this process? Well, you see from the picture that you can define the process inductively, like recursively, and say that Xn plus 1, number of individuals at generation n plus 1, is just equal to yn1 plus yn2 and so on up to yn xn. Okay? So for instance, if I go to the picture, I can say that x1 is equal to 2. Okay? And so x2 is going to be equal to the number of offspring produced by the first individual at generation 1 plus the number of offspring produced by the second individual at generation 1. And that would tell you that x2 is equal to y11 plus y12. And you stop here because in this case, x1, or this xn here, is indeed equal to just 2. So you stop here. And you don't have to use the other ones. So you just use the first xn of those random variables. Okay? So that's how you can have a rigorous definition of the process. You just take a doubly infinite collection of random variable y and I, all independent equal to k with probability pk. And then you only need to use a subset of them to construct your process. And among the y and I, you only need to use the first xn of them to eventually find the value of xn plus 1. That's how you construct your process. So now, notice that if xn equals 0, so that means that at time n there are no more individuals, or your graph just died, okay? Then in this case, you want xn plus 1 also to be equal to 0. If you have no more individual at generation n, then there is no potential parents that can produce offspring. And so if xn equals 0, xn plus 1 should be 0. That's implicitly in this expression. If xn equals 0, this sum is empty, and by convention, an empty sum in mathematics is equal to 0. So this expression is also valid when xn equals 0, and tells you that if xn equals 0, then xn plus 1 equals 0. Okay, so then notice also I explained here that from this expression, we can in fact say that the process is a Markov chain. So why is it the case? Well, that just because those y and I, they are independent of everything else, okay? They are independent of xn minus 1, xn minus 2, all those other random variables. And so you can write indeed xn plus 1 as a sum of random variables that are independent of everything else, but notice that the number of those random variables is equal to xn. So that tells you this expression, okay, the fact that those y and I are independent of everything else, this expression tells you that xn indeed depends, or xn plus 1 indeed depends on xn, but does not depend on xn minus 1, xn minus 2, xn minus 3, and so on. Okay? So this expression alone tells you that your process must be a Markov chain. Alright, so before we move on to the next step and look at the connection with martingales, I wanted to show you like simulation pictures that I created like using this algorithm here, and that can be like different realization, independent realization of your Galton-Watson branching process. In this case, for those pictures, I chose P0 equals 0.2, P1 equals 0.5, P2 equals 0.3. So that means that independently of each other, each individual is going to have 0 offspring with probability 0.2, 1 offspring with probability 0.5, and 2 offspring with probability 0.3. Now you see from the picture that it seems that the probability of survival is positive, and in fact we have some kind of exponential growth of the population. At the end of this video, just by looking at these numbers, you will be able to tell, yes, clearly in view of those numbers, it's clear that the process is a submartingale, and so the probability of survival should be positive. Looking at those numbers, you will even be able to compute explicitly the probability of survival of this particular process. Now let's look at how Galton-Watson branching processes are indeed connected to martingales, and this connection is going to motivate the distinction among subcritical, critical, and supercritical phases. Alright, so here I'm back to the previous slide. You see that we were able to express xn plus 1 using only xn and those independent, identically distributed random variables in the background. To check whether this process is a martingale or not, with respect to the natural filtration of the process, the idea is to look at the conditional expectation of xn plus 1 given fn, the natural filtration. Now, we already have an expression of xn plus 1 that depends on xn, which is fn measurable, okay? And those random variables that are independent of everything else. So having this expression should help to see whether we have a martingale or not, okay? And explore the connection between the process and martingales. So for that, I'm just going to look here at the conditional expectation of xn plus 1 given fn. Here, a key quantity that we are going to use is this mu here that is equal to the common expected value of all the YNI, common expected value, because they all have the same distribution. Alright, so if you look at this conditional expectation, you can just replace xn plus 1 by the expression we found before. Okay, that's what I'm doing here. And then also, instead of conditioning on fn, you can just condition on xn. Because we just proved that the process is Markov anyway. So Markov means that the probability of any event in the future given fn is equal to the same conditional probability, but given only xn. That obviously works also if you look at conditional expectation instead. So the conditional expectation of something in the future given fn is equal to the same conditional expectation but given xn. Okay, that's why I can replace fn by xn here. Now, if you look carefully at this expression, so you have a sum of random variables that are identically distributed, and they are all independent of xn. But the number of random variables I have here depends on xn. You have exactly xn of those random variables. We saw in chapter 2, at the very end of the video covering chapter 2, that in this context, okay, you can look at the condition for conditional expectation and so on, and we were able to prove that this conditional expectation obviously should be an xn measurable function, and in fact is just equal to xn times the common expected value of those random variables y and I. That's why I introduced this mu before. That's the key quantity. This conditional expectation is just equal to xn times the expected value of y and I, because those y and I are independent of xn, okay? And so eventually that gives you a mu times xn. All right. So this tells you at least that your Galton-Watson branching process xn is a martingale if mu equals 1, okay? Now, if mu is different from 1, we don't have a martingale. But clearly, if you look carefully at this calculation, that kind of tell you, and it's not surprising, that given the past, including the present, the expected number of individuals at generation n plus 1 is going to be equal to mu times the number of individuals you have at generation n. That's not surprising because mu is equal to this expected value, that's the expected number of offspring per individual. So that suggests that, or in fact you can prove directly because you have a martingale in the background, you can deduce from that that the expected number of individuals at generation n is going to be equal to mu at the power n. Because at each time step, you, on average, multiply the population size by mu, okay? So this calculation suggests that even if xn is not a martingale, it seems that if we rescale the population size, which is random, by its expected value, which is a fixed number, in this case mu n, we should get a martingale. And indeed, that works. If you use the fact that the conditional expectation is linear, okay, you divide on both sides by mu at the power n plus 1, what you get is that the conditional expectation of xn plus 1 divided by mu n plus 1 given fn is equal to mu times xn divided by mu at the power n plus 1, which simplifies and it gives you xn over mu n. So this calculation, even if it doesn't show that the process is always a martingale, it's only a martingale when mu is equal to 1, this calculation tells you that hidden behind this process xn, you have indeed a martingale that you get after rescaling by the expected value of the population size at time n, and you conclude that the rescale process xn over mu at the power n is a martingale. Okay, that's a property we are going to use to study the subcritical phase and the critical phase. From that, we can tell that because the expected value of a martingale is constant, and clearly if you take n equals 0, you get x0, which is equal to 1, divided by mu at the power 0, that is again equal to 1. This tells you that expected value of xn over mu at the power n is constant equal to 1, and so the expected value of xn is equal to mu at the power n. Okay, that's a property we are going to use soon. Okay, so we get this. Then, going back to this expression, without looking for exactly a martingale, we can, from this expression, also say clearly that, depending on the value of mu, xn is going to be indeed either a super martingale or a martingale or a sub-martingale. Okay? Because that's a positive process. Clearly, if mu is less than 1, okay, we are going to get that this conditional expectation is less than xn. In this case, we have a super martingale. If mu is more than 1 at the opposite, this conditional expectation is larger or equal to xn, and then we get, in this case, a sub-martingale. Obviously, when mu equals 1, we get a martingale. Okay? So we have those three different regimes that depends on the value of mu. This is not really surprising. Okay? I told you that the different types of behavior that the process xn can display depends on this offspring distribution. Now what we learn is that this, like the limiting behavior of the process, is going to depend on this offspring distribution, but only through its expected value. Because the expected value of yi is the expected number of offspring per individual. And so it's kind of not surprising, I mean, it's kind of intuitively clear that if this mu is 1, then on average, the process is not going to move, so we should have a martingale. But if on average, individuals have more than one offspring, we expect to have a sub-martingale, a process that tends to go up. At the opposite, if mu is less than 1, expected number of offspring per individual is less than 1, then in this case, we expect the process to go down on average and have a super martingale. Okay? So the distinction is here. We just said that clearly we have a super martingale, martingale, or sub-martingale, depending on whether mu is less than 1, equal to 1, or larger than 1. And starting from now, I'm going to call those three cases respectively subcritical phase, critical phase, and supercritical phase. So now from the fact that xn over mu n is a martingale, we can easily deduce that in the subcritical phase, we have exponential decay of the population. And so here is the proof that just one line. I assume that we are in the subcritical phase where mu is strictly less than 1. And I'm going to look at the probability that xn is larger than 0. So strictly larger than 0, so that means exactly this is exactly the probability that the population is not dead yet at time n. Okay, that's the probability that the time to extinction is larger than n. Alright, so first I'm going to use the fact that xn strictly larger than 0, because that's an integer valued process, means exactly that xn equals 1, or xn equals 2, or xn equals 3, and so on. Those events are mutually exclusive, okay? And so by sigma additivity of the probability measure, I can just say that this event, which is like an infinite union, is just the infinite sum for k larger than 0 of the probability that xn equals k. Alright, so then, next step, I just said that this is bounded by the same sum, but where I inject a k here. Again, this is obvious. Here, I'm just multiplying each of those terms that are all positive by an integer that is worst case scenario equal to 1. Okay, k can be equal to 1, 2, 3, and so on. So I can only, doing that, I can only increase this sum here. Okay, but then you see that if I replace k strictly positive by k larger or equal to 0, I don't change anything because this term anyway would be equal to 0. You would have a 0 times the probability that xn equals 0. Okay, so I can do that, and then I make it clear doing that this infinite sum here is exactly by definition the expected value of xn. Okay, and so eventually we get that the probability that xn is larger than 0, which is the probability that the time to extinction exceeds n, is less or equal than the expected value of xn. Okay? So to get this inequality, you can do it directly by using Markov's inequality also. Okay? I remind you that Markov's inequality tells you that the probability that a positive random variable is larger than epsilon is less than the expected value of this random variable divided by epsilon. Okay? If you do this for epsilon equals 1, in this case you get that the probability that xn is strictly positive is the same as the probability that xn is larger or equal to 1, which by Markov's inequality is less than the expected value of xn divided by 1, which is just the expected value of xn. Okay, I prefer this approach because here we just use the definition of the expected value and sigma additivity that are basic properties, while Markov's inequality is something a little bit more sophisticated. This proof here is, I would say, more transparent. Alright, so then, last step, you see that we just proved that xn over mu n is a martingale, okay? Which means that, in particular, the expected value of xn over mu n is constant, equal to 1 in this case. And so that also tells you that the expected value of mu n is, of xn is equal to mu n. Okay. Then notice that here, never in this calculation I use the fact that mu is less than 1. That's true for all mu. But of course, that's only interesting, that's only useful if mu is less than 1. If mu is larger or equal to 1, then of course this mu at the power n is going to be larger or equal to 1, and the inequality just tells you that this probability is less or equal to 1, which we know already a probability has values in the interval 0, 1. So even if this calculation is true for any mu, okay, that's only useful in the case where mu is less than 1. Okay, so now you see that if mu is less than 1, obviously this mu at the power n is going to converge to 0, and it goes to 0 exponentially fast. And so that means that the probability that xn is larger than 0, which is again the same as the probability that it takes more than n units of time or more than n generations to have extinction, is going to be less than something that goes to 0 exponentially fast. And so from that we can conclude that indeed when mu is less than 1, the population goes extinct exponentially fast. So now let's study the limiting behavior of the process in the critical phase, and like I told you at the beginning of this video, in this case the limiting behavior is much more surprising, and in fact we can prove that the cumulative number of individuals across time is almost surely finite but infinite on average. Alright, so more precisely, so I'm going to study the critical phase, so the case where the expected number of offspring per individual is equal to 1, but I'm going to exclude the case where P1 equals 1, okay? This is an exception. This case is trivial and also boring because the sum of the pk is equal to 1. These are the terms of a probability mass function that add up to 1, saying that P1 equals 1 means that all the other pk's are equal to 0. And so that means that at each time step, each individual is going to give birth to exactly one offspring with probability 1. So in this case, if you start with one individual, you are going to have one individual at all time. In some sense, your stochastic process becomes deterministic. It's not really exciting. Okay, so now before I show you the proof, I want to give you some kind of intuition on the reason why, if we assume that P1 is different from 1, but still the expected number of offspring per individual is equal to 1, why in this case, intuitively, we kind of expect extinction. So the idea is that if P1 is different from 1, the only way you can make the average equal to 1 is if P0 is strictly positive, and some of the pk's for k larger than 1 also must be positive. Okay? Now, if P0 is strictly positive and some of the pk's are for k larger than 1 are positive, then that tells you that your process is going to fluctuate in some sense. It's going to show those random fluctuations. Okay? But also because in this case you have a martingale, we kind of assume that the process is not going to take off. So if your population does not take off, and so is kind of bounded, but displays those kind of random fluctuation, you kind of expect that at some point it's going to crash to 0, and then you have extinction. And that's indeed this kind of intuition, that's indeed what you see in the proof. Alright? So, now how can we prove that rigorously? To prove almost sure extinction, first, you want to prove that xn converges almost surely to 0. The first theorem we saw about almost sure convergence of martingales is the martingale convergence theorem. And to be able to apply this theorem, we need to prove that the process is bounded in L1. So that's the first thing we need to do. And the proof is very simple in this case. You just look at the L1 norm of xn, okay? Then, because your process is positive, that's a number of individuals, absolute value of xn is equal to xn itself, so the L1 norm of xn is just equal to the expected value of xn. Now, because you have a martingale, we know that the sequence of expected values is constant, and so in particular, expected value of xn is equal to the expected value of x0. And this is just 1, that's our assumption. But if you assume more generally that x0 can be whatever, as long as it's finite, then you get a uniform bond for the L1 norm of xn. Okay? This is finite, so even if you take the supremum is still equal to the expected value of x0, which is finite, and so the process is bounded in L1. So we have our assumption for the martingale convergence theorem. And then from that, we can deduce at least that xn converges almost surely to a random variable that is integrable. Right. So, before we go further, I want to point out something interesting here. If you look at this calculation, we never used that Xn was a Galton-Watson branching process. The only thing we use is one, that Xn is positive, and two, that Xn is a martingale. And in fact, if you follow this reasoning, you would see that this applies to any positive martingale. Okay? And so, from this reasoning, you can conclude some pretty strong result that you might want to use in practice. It's the fact that a positive martingale is always bounded in L1, and so is going to always converge almost surely to an integrable random variable. Okay? It's not true if your martingale is not positive. Okay? So for instance, if you look at the one-dimensional symmetric random walk, that's a martingale, but that's not positive. Your one-dimensional symmetric random walk is not going to converge almost surely to a random variable. Okay? But if your martingale is positive, then you can conclude that. Alright, so now let's go back to our Galton-Watson branching process. And now what we want to do, next step, now that we know that there is a limit almost surely, what we want to do is prove that this x infinity is in fact almost surely equal to 0. Okay, and so for that, I'm going to take a k, an integer k strictly positive, look at the probability that x infinity is equal to k, and we want to prove that this is 0, and then that's going to tell us that the only possible value for this random variable is 0. Notice that those xn are integer valued, and so that means that the limit also needs to be in the set of natural numbers. So how do we prove that indeed this random variable cannot be strictly positive? So the reasoning is here. So again, I'm assuming that P1 is different from 1. That's important to conclude that this probability here is 0. I'm going to fix a k strictly positive. I'm going to look at the probability that this random variable, like the limit, is equal to k, to prove that x infinity is equal to 0, and so that we have extinction. What we need to prove is that this probability is equal to 0. Okay? Then, if I just use the definition of limit almost surely, saying that x infinity is equal to k is exactly the same as saying that the limit of the xn is equal to k. So we want to prove that the probability that the limit equals k for all k strictly positive is equal to 0. Right. So to conclude that, a key assumption in the model that we need to use is the fact that xn is integer valued. Okay? Xn can only be an integer. Okay? And then one particularity of sequences of integers that converge to a limit is that the time it takes to go to the limit is not infinite. It's going like your sequence is going to reach the limit in a finite time. So why is it true? Well, just go back to the definition of limit. Okay? Let's assume that xn goes to k, converges to k. Then this means that for all epsilon, there exists n large enough such that, or I should say for all epsilon, the absolute value of xn minus k is going to be less than epsilon for all n large enough. Okay? But if you take your epsilon equals 1/2, for instance, if the distance between two integers, okay, xn is an integer and k is an integer, saying that the distance between two integers is less than 1/2, that means that those two integers must be equal, okay? And so eventually, just applying the definition of limit, okay, for a sequence of, like a basic sequence of real numbers, this tells you that if your sequence is integer valued, okay, then you can say that for n large enough, xn is equal exactly to k. Okay, and so from that we can go from this step to this step and say that if the limit is k, that means that there exists some capital N such that xn is equal to k for all little n larger than capital N. In this event here, capital N is a random variable, but it says that the time it takes for xn to reach k and stay there should be almost surely finite. That's an almost surely finite random variable n. Now, if you look carefully at this event, you realize that this is not possible. So why this is not possible, or at least this happens with probability 0, I should say. This is not possible because we assume that P1 is different from 1. So again, that means to have a mu equals to 1, we need P0 strictly positive, and some of the pKs for k larger than 1 strictly positive also, which means that the process should fluctuate. So it's not possible that the process gets stuck at the value k forever. It can stay at the value k a little bit, an arbitrarily large number of steps in fact, but eventually, because there is a positive probability that individuals do not have any offspring or have more than one offspring, eventually it's not possible that this xn does not evolve like that. Okay? So that shows that this event has probability 0. Okay? And so if you go back, that says that for all k positive, the probability that x infinity equals k equals 0. So the only possible value for x infinity, that's going to be 0. So x infinity is equal to 0 with probability 1, almost surely, which shows indeed extinction. Okay? Eventually, we get that xn converges almost surely to 0. Notice that, again, this martingale convergence theorem tells you limit almost like a convergence almost surely to a limit. The presence of fluctuation says that this is not possible, so the process should get stuck at some point. And the only way you can indeed get stuck, which is consistent with the conclusion here, is if you are at 0. If you are at 0, indeed, you don't move anymore. But as long as you have individuals in your process, again, because P0 and one of the pk for k larger than 1 are going to be positive, then you must have those fluctuations. As long as you have individuals, you must have fluctuation. The only way you do not see those fluctuations is if your process is already at 0. All right, so this shows that you have extinction with probability 1, okay? And so in particular from that, you can deduce that the total number of individuals in your process, okay, the cumulative number of individuals across time, which is basically x0 plus x1 plus x2 plus x3 and so on, this total number of individuals should be finite, almost surely, okay? You have extinction in a finite time, so the total number of individuals should be almost surely finite. Still, we can prove using the monotone convergence theorem that this total number of individuals is infinite on average. And the proof is simple, that just follows from a basic direct application of the monotone convergence theorem. So I'm reminding you this quantity here. I'm looking at the infinite sum of the xn. That's exactly number of individuals at generation 0 plus number of individuals at generation 1 plus number of individuals at generation 2 and so on. So this infinite sum here is indeed the total number of individuals in your process across time, the cumulative number of individuals. Convergence almost surely to 0 here shows that this random variable, this infinite sum, must be almost surely finite. But if you look at the expected value of this, same story as what we used many times. You can say that this infinite sum is the limit of the partial sums, but those xn are non-negative, so the sequence of the partial sum is monotone. Then you can use the monotone convergence theorem if you think of this as the limit of a sequence of random variables, and this sequence is monotone, non-decreasing. then you can use the monotone convergence theorem and say that the expected value of the infinite sum is equal to the infinite sum of the expected values. Okay? But it's still written here because you have a martingale. The expected value of xn is equal to the expected value of x0, which is 1. Okay? So this is in fact the infinite sum of expected value of x0, which is an infinite sum of 1s, so that's equal to infinity. Okay? So conclusion, in the critical phase, excluding the case where P1 equals 1, in which case the process is just deterministic, excluding this case, we conclude that the cumulative number of individuals in the process is almost surely finite, but infinite on average. And so what this shows is that, like in the subcritical phase, we have indeed almost sure extinction. But unlike in the subcritical phase, because this expected value is infinite, we do not have exponential decay of the population. So finally, let's look at the supercritical phase. This case is less surprising than what happens in the critical phase, but still the mathematics we are going to use to study this phase is pretty rich. And to begin with, I'm going to define the notion of probability generating function of the offspring distribution, and we are going to see how we can use this function to better understand the probability of extinction of the process. All right, so we are in the supercritical phase. Mu is strictly larger than 1. The expected number of offspring per individual is strictly larger than 1. In this case, the process is a submartingale. We define the probability generating function of a random variable, and in this case, I'm going to look at the probability generating function of those random variables y and I. So this is defined as a function g of theta, where theta is a real number. And that's equal to the expected value of theta at the power y and I. Okay? So the outcomes of those y and I may be different, like that's what we use to build this tree. Here, that's the 2, 3, 1, and so on. But all those y and I have the same probability mass function. They have the same distribution, which means that this expected value here, in fact, does not depend on n and I. This function is always the same for all n and I. That's only a function of theta. Okay? Now, if you look at the definition of expected value, you can express that more explicitly. Y and I can be equal to 0, 1, 2, 3, and so on, which means that theta at the power y and I can be equal to 1 theta, theta square, theta cube, and so on. And that's equal in general to theta at the power k with probability pk. And so this expected value is just equal to the infinite sum of pk times theta at the power k. Okay? So depending on the choice of the pk, it's possible that this sum in fact is finite, in which case this function is just a polynomial. But a priori, it's possible that all the pk are positive. And in this case, you have an infinite sum here. So that's some kind of generalization of the notion of polynomial. And this type of function is called a power series. So I need to say a few words about power series, a few properties about power series that we are going to use after. So after, we are only going to look at this function when theta is between 0 and 1. This parameter theta is going to be interpreted as a probability. So we want to understand this function in the interval 0, 1. Notice that clearly, because the pk's are non-negative, this function is going to be increasing or non-decreasing at least. So the maximum value is at theta equals 1. If you take theta equals 1 here, you look at g of 1, you get infinite sum of the pk. Okay, 1 at the power k is just 1, so you get infinite sum of the pk. That's exactly the sum of the terms of a probability mass function, so that's just equal to 1. So this shows that for all theta between 0 and 1, this sum here, or g of theta, is less or equal to 1. property of power series, because that's bounded on the interval 0, 1, it turns out that this type of function is called an analytic function. And those functions are basically smooth functions. They are not only continuous, you can also differentiate this function and in fact differentiate the function as many times as you want. And a very important theorem in real/complex analysis about power series is the fact that on the domain where the function is bounded, okay, that we call, if theta was a complex number, the disk of convergence of this function, it turns out that the derivative of this sum is equal to the sum of the derivatives. Okay, that's an important theorem in real analysis, complex analysis. Notice that it has some similarities with the monotone convergence theorem and the dominated convergence theorem in measure theory, in the sense that this property is again about exchanging two limits. Okay, the monotone convergence theorem and the dominated convergence theorem gives you conditions under which you can exchange limit and integral. But an integral, in some sense, is a limiting object. Okay, here it's kind of the same idea. You have an infinite sum, but looking at the derivative is also like looking at a limit. And when you deal with a limiting object like that, it's not clear that you can exchange things. And it's not always true that the derivative of an infinite sum is equal to the infinite sum of the derivatives. But in this case, that works because we have a power series, an analytical function. Okay? So keep that in mind. This function, that is like a generalization of the notion of polynomial with degree infinity, potentially, is in fact a very smooth function. And to look at the derivative of this function, I can just look at the sum of the derivatives. That's a property I'm going to use after. All right, so that's the probability generating function of the offspring distribution. Then the probabilities of interest we are going to look at now also are the probability of extinction by time n, which I define as the conditional probability that xn equals 0, so you have extinction before time n, given, I remind you, that we start with one individual, okay, at time 0. I'm going to call this probability theta n. Now, it turns out that this sequence theta n is related to this function g here, okay? And so the idea is going to be to look at theta n plus 1, try to express theta n plus 1 as a function of theta n, okay? And then we will see that somewhere just this function g just pops out like that, okay? So, how can I express theta n plus 1 using theta n as a function of theta n? Well, this kind of technique is like typical in the theory of Markov chain, and it's based on something called a first step analysis. Okay, that's a typical technique that you can use to express this probability at some given time using probabilities at the previous time. And so the idea here is just the idea of a first step analysis is just to look at this probability but condition on what happens at the first step, and in this case it's going to be through a conditioning and we are going to condition on the random variable x1. Okay, that's again a typical technique. We saw that in fact in chapter 2 that just how you can compute the probability of an event by conditioning on a partition, and this is just a variant of this technique where you condition on everything that can happen at the first step. So that's called first step analysis. Okay? So if we do this, we clearly obtain that theta n plus 1, okay, which is by definition the probability that xn plus 1 equals 0 given that x0 equals 1, okay, can be written that way. I'm just conditioning on all the possible values of the process at time 1, okay? At time 1, the process can be equal to the number of individuals at generation 1 can be equal to 0, 1, 2, 3, and so on. That forms a partition of omega. Conditioning on this partition, then I can write that theta n plus 1, which is the probability that xn plus 1 equals 0 given x0 equals 1, is in fact the same as the sum over k of the probability that xn plus 1 is 0, so your event of interest, but given x1 equals k, times the probability that x1 equals k, and you can add here given that x0 equals 1. Okay? So, doing this, you see that we go from a probability that involves something that we call a transition probability in the theory of Markov chain. So, from time 0 to time n plus 1, so that's n plus 1 time steps. I'm rewriting that into a 1 time step here from time 0 to time 1, but then a n time step here, going from time 1 to time n plus 1. And it turns out that this conditional probability can be expressed using only theta n. That's kind of the idea of this technique. So let's look carefully at those two probabilities. What is the probability that x1 equals k, given that x0 equals 1? Well, that's just pk. By definition, that would be the probability that this first individual here gives birth to k offspring. That happens with probability pk. So this probability is just pk. Now this conditional probability is more interesting. In this case, again, have in mind that because things are homogeneous in time, okay, the rules of the process, like the number of offspring per individual, does not change in time. Okay, this YNI is always the same in distribution for all n. So that means that the probability of going from k individual at time 1 to 0 individual at time n plus 1 is the same as going from k individual at time 0 to 0 individual at time n. Okay? So that's exactly like looking at n time steps of your branching process, of your Galton-Watson branching process. Okay? So, now to understand this better, let's look at this picture, and you will see that from the topology of the tree, you can kind of better understand this conditional probability. So, in this picture, the first individual gives birth to 2 individuals. So that corresponds to the case where k equals 2. Here we have 2 individuals at generation 1. And so, what is the probability that at time n plus 1, we have no more individuals if we have 2 individuals at time 1? If you look carefully at your tree, you see that this part of the tree, this subtree here, does not overlap this subtree here. These are 2 independent pieces of the tree. This one is generated by random variables, y and I, that are independent of the random variables used to generate this part of the tree. Okay? So that means that the family of this individual and the family of this individual, they are independent, identically distributed Galton-Watson branching processes with, again, the same offspring distribution. Okay? So, saying that this process, this tree here, is going to die before time n plus 1, that means exactly that each of those 2 trees, okay, is going to die in less than n units of time. But because each of those 2 trees are like 2 Galton-Watson trees that are independent, again generated by the same offspring distribution, what you can say is that the probability of extension of this tree by time n plus 1, given that we start with 2 offspring, okay, for the first individual, is exactly the probability that this tree dies out in less than n units of time, times the probability that this tree dies out in less than n units of time. But they are identically distributed, so that's exactly the probability that you die out starting from 1 individual in n units of time, but you have to multiply that by itself like 2 times here, or in general k times if you have k individuals. Okay, so all that is just to say that the probability that if you have K of spring at the first place, the probability of extinction by time n plus 1 is exactly the probability that one Galton-Watson branching process starting with one individual dies out in n unit of time, and this at the power k. You can just look at the power by independence, okay? And so eventually you can simplify a little bit this expression, and again this is pk, and this one is exactly the probability of extinction in less than n unit of time, okay, of k independent Galton-Watson branching process. So that's exactly the probability of extinction in less than n unit of time, starting with one individual, but at the power k, okay, using the fact that the corresponding k subtrees do not overlap and therefore are independent, okay? All right, so we have this. Now, we're almost done here to see that indeed that's related to this function g. This probability that you go from one individual at time 0 to 0 individual at time n, that's exactly this probability theta n here. So I can replace that by theta n, and that tells me that theta n plus 1 is equal to the infinite sum of pk times theta n at the power k. But that's exactly the expression of g of theta for theta equals theta n, okay? And so eventually we can conclude that theta n plus 1 is equal to the infinite sum over k of pk times theta n at the power k, which is exactly g of theta n. All right? So that tells you that this sequence of probabilities can in fact be defined recursively using this function g, okay? The probability at time n plus 1 is equal to g of the probability at time n, alright? Okay, so now, next step, we have here the probability of extinction by time n. This relates to the probability of extinction at some time in general. In fact, this sequence theta n is going to converge to a limit that is exactly equal to the probability of extinction of your process. To prove that, we can use again the monotone convergence theorem. So first, notice that the sequence of events xn equals 0 is a monotone sequence, because if xn equals 0, of course xn plus 1 is going to be equal to 0. So this sequence of events is non-decreasing. Because this sequence is non-decreasing, this sequence of event non-decreasing for the inclusion, if you look at the probability, and so you look at the sequence theta n instead, then you define a monotone sequence, but this time of real numbers, okay? The sequence of probability is going to be non-decreasing, and obviously that's bounded by 1, because that's a probability. Okay, so if you have a monotone sequence that is bounded, then this must have a limit. Okay, so theta n is going to converge to a limit. I'm going to call this limit theta infinity. That follows from the fact that the sequence theta n is monotone. Okay, now next step, we want to prove that the limit of the sequence theta n, which we call theta infinity, is indeed equal to the probability of extinction of the process. And to do this, it's just a problem of exchanging limit and probability, which we can do by the monotone convergence theorem, because we just proved that this sequence of events is monotone. Okay? The event that xn equals 0 is going to be an increasing sequence in n. Okay? And so eventually we get by the monotone convergence theorem that this limit, by definition, that's the limit when n goes to infinity of the theta n, that's the limit when n goes to infinity of the probability that xn equals 0. Okay? But by monotonicity of the sequence of events, monotonicity for the inclusion, you can put the limit inside, and so that tells you that this is equal to the probability that the limit when n goes to infinity of xn is equal to 0. Here, it's like I exchange a limit and an expected value. If you think of the probability as the expected value of the indicator function, but because those events are monotone for the inclusion, then the corresponding sequence of indicator function is monotone as a sequence of actual functions. So that's why you can use the monotone convergence theorem. But clearly, if you look at this event, the event that xn converges to 0, that's exactly by definition the event that the population goes extinct. Okay? And so we have that the limit of this sequence is indeed the probability of extinction of your Galton-Watson branching process. Okay? So if you put things together to sum up, we have a sequence here whose limit is exactly the probability of extinction of the process. But this sequence can be defined recursively by applying the function g, okay, several times. So from that, it seems that this probability of extinction, theta infinity, should be a fixed point of this function. Okay? And indeed, we can prove that. The only trick we have to use in the next reasoning is the fact that, again, this function is Power series analytic smooth function, so this is continuous. Okay, the function g is continuous. And so using this, we also have that g of theta infinity. I just replace theta infinity by its definition, that's the limit of the theta n, so that's equal to g of the limit of the theta n, by continuity of the function, okay, on the interval 0, 1, and clearly this theta infinity, that's a probability that's going to be between 0 and 1. So this g of the limit by continuity is going to be equal to the limit of g of theta n, okay? But we proved here that g of theta n is also theta n plus 1. So this is also the limit when n goes to infinity of theta n plus 1, which again is equal to theta infinity. Okay? So conclusion, we have that g of theta infinity is equal to theta infinity. So what we proved so far is the fact that the probability of extinction of a Galton-Watson branching process must be a fixed point of this probability generating function. So now that we have this result, we can study the supercritical phase and prove that the probability of survival is indeed strictly positive. In fact, we can also have some implicit expression of the probability of survival. All right, so I just remind you what we just proved in the previous slide. In the supercritical phase, the probability of extinction here is going to be a fixed point of the probability generating function g. Because theta infinity is the limit of the theta n, and the theta n are probabilities, and so between 0 and 1, we only need to understand this function on the interval 0, 1. Okay, we only need to look at the fixed point, the potential fixed point of this function in the interval 0, 1. All right. Now you see also that if theta is between 0 and 1, those theta k are between 0 and 1, and so this function must be non-negative, but also this function on the interval 0, 1 is bounded by this infinite sum of the pk. We saw that it's equal to 1. So the function, like what we can say is that for all theta between 0 and 1, g of theta is again between 0 and 1. Okay? So we only need to understand the graph of the function on this interval, and we know that the graph is going to be somewhere in this unit square. Okay. In this picture, I also draw the diagonal, like the straight line with equation x equals y, because geometrically the way you find the fixed point is by looking at the points where the graph of your function is going to intersect this straight line. Okay, that's why I have this straight line. All right, so first let's look at particular values of the function at 0 and 1. We can also study looking at the derivatives We can study the monotonicity of this function, convexity, and so on. And doing all that, we'll be able to find where are the fixed points, or at least existence uniqueness of those fixed points. All right, so first, let's look at the value at theta equals 0. If theta equals 0, theta de power k is always 0, except when k equals 0, this becomes 1. And so in this case, g of 0 is equal to just p0. Okay? Then, over particular value, what happens when theta is equal to 1? Well, when theta equals to 1, theta de power k is always equal to 1. And so g of 1 is equal to the infinite sum of the pk, because again, these are the terms of a probability mass function, they add up to 1. So g of 1 is equal to 1. So we get those two particular values. First, g of 0 is equal to p0 and g of 1 is equal to 1. And so that tells you for the graph of the function that we have something like that. We start at p0 here and we end up at 1 here. Alright, so the p0 here in the picture, I'm taking it strictly between 0 and 1. Notice that indeed p0 cannot be equal to 1. If p0 equals 1, that means that all the individuals give birth to 0 offspring with probability 1. In this case, mu would be equal to 0, okay? But we assume mu is strictly larger than 1. To be in the supercritical phase, we cannot have p0 equals 1. Now, we can have p0 equals 0, okay? That's a possibility. But if p0 equals 0, that means at the opposite that individual must have at least one offspring. And in this case, it's obvious that we will have survival with probability 1. So I'm excluding the case p0 equals 0 in the picture because that's just trivial. Okay, that's not that we don't know how to do it, that's just easy, that's trivial. So the case that is non-trivial is when p0 is strictly between 0 and 1. Okay, so 0 is trivial, 1 is not possible, so I'm taking p0 in between. Then, next step, how do we connect those 2 points? Okay, what is the behavior of the function in between? Here I don't really know, I just drew those little things here, but can we say something about the monotonicity of the function and the convexity of the function? The answer is yes, and again I'm going to use the fact that this is an analytic function, and so we can differentiate the function as many times as we want, and the sum of the derivatives is equal to the derivative of the sum, okay? And so doing this, we can easily study the monotonicity and convexity by looking at the second derivative of this function. Okay, so first, to study the derivative, first and second derivative of this infinite sum, notice that we can say something about those pk, about whether they are strictly positive or not. What we can say is that pk must be strictly positive for some k larger than 2. There is at least one k larger than 2 such that pk is strictly positive. Okay? If it's not the case, that would mean that the only 2 pk's that are strictly positive are p0 and p1. But if only p0 and p1 are strictly positive, then mu again should be less or equal to 1. But we assume mu is strictly larger than 1. So individuals must be able, with positive probability, to give birth to strictly more than one offspring. Okay? So we must have, again, pk strictly positive for some k larger or equal to 2, because we are in this case. Now, using this property, we can deduce that the first and second derivative of the function are both strictly positive, as long as theta is strictly positive. The way you compute the derivative, like I told you, is just by saying that the derivative of the sum is equal to the sum of the derivatives, even if the sum is infinite, because the function is analytic. So here, the derivative of that is equal to the infinite sum of the derivatives, but the derivative with respect to theta of theta at the power k, that's just k times theta at the power k minus 1. So that gives you this sum here. Now, to compute the second derivative, you are just going to look at, again, the derivative of this infinite sum, but the derivative of theta at the power k minus 1 is k minus 1 times theta at the power k minus 2, which gives you this expression here. Okay? Okay, so notice that this k here is 0 if k equals 0. And this product k minus 1 is equal to 0 if k equals 0 or 1. But we just saw here that pk must be strictly positive for some k larger or equal to 2. So that means that implicitly, like this sum start at k equals 1, this one start at k equals 2. But after k equals 2, we must have at least one positive term. So if we also assume that theta is strictly positive, then that indeed makes those two sums strictly positive. Okay? And so those two properties show that the function is strictly increasing in the interval 0, 1, and this one tells you that the function is strictly convex on the interval 0, 1. Okay? So we can deduce this, increasing convex, and so that tells you that the graph of the function is going to connect those 2 points by only going up and in a convex manner, and so only 2 possible options are those 2 options. Okay? Either your graph, your curve here is going to stay above the straight line x equals y, or it's going to cut the straight line and then go up to the point 1, 1. That's those 2 possibilities that happen from our analysis here. Right, so because theta infinity is a fixed point, that's the probability of extinction, is a fixed point of this function, and we want to prove survival with positive probability, we want to exclude this fixed point, 1, as the unique fixed point of this function. So what we want to do at this point is say that the scenario at the top here, like the case where your graph is only going to intersect your straight line at point 1, is not what we want. What we want is this other case here. So how do we exclude this case and say that no, what indeed happens is the fact that this graph is going to intersect this straight line strictly between 0 and 1, which hopefully will make this theta infinity a number that is strictly between 0 and 1 and not this point 1 here. So if you look carefully at your 2 scenarios here, you see that if you intersect the straight line, okay, and then you go up like that to this point 1, 1, then in this case, the derivative at point 1, 1, at point 1, should be strictly larger than 1. Okay? That's a characterization of all those graphs here that are going to intersect the straight line between 0 and 1 and again at 1. At the opposite, if you look at all the graphs that are above, okay, then in this case you see that the derivative here, so that you can intersect indeed here, coming from above, the derivative here should be less than 1. Okay? So to exclude this case and show that this is indeed what happens, what we need to prove is that the derivative at point 1 is strictly larger than 1. Okay? So now if you look at the derivative at 1, what do we get? Well, the derivative is still written here. Okay? If you take theta equals 1 here, you get infinite sum of kpk. Infinite sum of kpk, that's exactly the expected value of your offspring distribution. But by assumption, the expected value is mu is strictly larger than 1. So in fact, the derivative at point 1 is equal, okay, by this calculation, is equal to exactly mu, but by assumption we are in the supercritical phase. Mu is strictly larger than 1. Okay, so that means that this case here where the graph stays above the straight line on the interval 0, 1 is not possible. That would make the derivative less than 1. So what happens, in fact, is the scenario at the bottom here. So we can conclude that the graph of G intersects the diagonal once in the interval 0, 1 open at 0 and 1. And so what really happens is that. Okay? Alright, so now because we don't have an explicit expression of the pk, obviously we cannot exactly say what is the fixed point, what is the value of the fixed point. That depends strongly on the choice of the offspring distribution. But at least what we can say is that for any possible choices of the offspring distribution, if the expected value is strictly larger than 1, then the graph of the probability generating function should look like that. It should start in this interval 0, 1, should end up at point 1, 1, should be strictly convex, also strictly increasing, and so that's going to cut this straight line at only 1 point. Okay? The fact that we have at least one fixed point in between comes from the fact that the derivative here is strictly larger than 1. Okay, that's the last thing we did. The fact that there is uniqueness of this fixed point follows from the convexity of the function. Okay, if you think about it, the only way this graph is going to intersect this straight line twice between 0 and 1 is if you kind of cut it like that, but then you would have, you cut the graph like that, but then to go back here, you would have to change the convexity. Okay? If you cut it twice here, you have to change the convexity of your function, but no, the function is convex. Okay? It's nowhere concave, so that's the only possibility. Convexity shows that there cannot be more than one fixed point, but derivative here at 1 larger than 1 says that there is at least one fixed point. Okay? And so combining the two, we have existence and uniqueness of a fixed point between 0 and 1. Right. So now the point is that it still doesn't say, okay, what we know so far is just that theta infinity is a fixed point of the probability generating function, and this fixed point is between 0 and 1. So that can still be this fixed point or this fixed point. So what is it? Okay? If theta is equal to this fixed point, 1, that's not good because probability of extinction is 1 and so probability of survival is 0. That's not what we want to prove. But if we can prove that this is indeed the limit theta infinity, then we are done. Okay? And it's indeed the limit of theta of the sequence theta n, so that's indeed theta infinity. And the way we prove that is just by constructing graphically the sequence theta n. So if you have a sequence theta n defined by g of theta n plus 1 is equal to g of theta n, then one way you can construct the sequence graphically is, like from the picture here, is by saying, well, first you observe that theta 0 is equal to 0. The probability of extinction at time 0 is 0 because we assume that we start with one individual. So at time 0 we do not have extinction. So theta 0 is equal to 0. Then the way you find theta 1 by the fact, by the previous slide that says that theta n plus 1 is equal to g of theta n, this tells you that theta 1 must be equal to g of theta 0. Okay? But g of theta 0, you already it here. Okay? That's p0. p0 is equal to theta 0. And then the way you find theta 2 is by again applying g, and so theta 2 is g of theta 1. And the way you do this is you just project this on the straight line here, and you go up again. And here you read theta 2. And then you go here again and look at the image by the function g, that's theta 3, and so on. And then eventually, you can see that your sequence looks like that. You have theta 0, then here theta 1, then here theta 2, then here theta 3, and so on, and then you see that eventually theta infinity is indeed this fixed point, okay? So there is this nice geometric interpretation of a sequence like defined recursively from a function. You have this nice way of drawing basically your sequence using the graph of the function, okay? All right, so we are done. We proved that theta infinity is we prove first that this function, because mu is larger than 1, has a unique fixed point strictly between 0 and 1. That's the first thing we proved in this slide. And the second thing here with this picture that we proved is that theta infinity is indeed equal to this unique fixed point that is strictly between 0 and 1. So that means that the probability of extinction is strictly between 0 and 1. And so the probability of survival, which is 1 minus theta infinity, of course is again strictly between 0 and 1. So conclusion, the probability of survival, which is 1 minus theta infinity, is indeed strictly positive. Okay? So all this work was to prove that if mu is strictly larger than 1, indeed the probability of survival is strictly positive. But along the lines, we proved way more than just the fact that this probability is strictly positive. We know that this probability is equal to 1 minus the value of the unique fixed point of this function, okay, in the interval 0, 1, okay? And so that means that in practice, so of course now we cannot do much more because those pk are not given, but if you have an explicit expression of the pk, you can sometimes compute explicitly this probability of survival, okay? So to conclude this video, now I'm going to give you like some kind of tricks you can use to compute actually like this fixed point and deduce the probability of survival, okay? And then I'm going to go back to the example I showed you before, and we can solve that one explicitly. All right, so first you see that to be able to find theta infinity, what you have to do is find this fixed point of the function g of theta. And so that's the same as finding the zeros of the function g of theta minus theta. Okay, you want to solve g of theta minus theta equals 0. Okay. Now let's assume that only p0, p1, and p2 are strictly positive. All the other pk's are equal to 0. Then in this case, this function here is just a polynomial with degree 2. Okay? So you can easily find the zeros of g of theta minus theta by just looking at the discriminant and so on. Okay? So that's an easy case. If your individual can only give birth to 0, 1, or 2 offspring, then we know how to find the exact solution of like this equation here. We can find exactly theta infinity. All right. Then assume now that also P3 is strictly positive, okay? But all the other ones are equal to 0. Then in this case, you would have to solve to find the zeros of a polynomial with degree 3. We know that there are solutions. We know how to express them. It's just impossible to do it by hand. It's too long. It's too complicated. But in fact, you can again do it easily. So that's a trick you can use in practice. If g of theta is a polynomial with degree 3, meaning that your individuals in your population, they can give birth to 0, 1, 2, or 3 offspring, but nothing else, then you end up with a polynomial with degree 3 that g of theta minus theta. But the theory here tells you that, well, g of 1 is equal to 1, okay? So theta equals 1 is a zero is a root of your polynomial g of theta minus theta. And so the theory of polynomials tells you that g of theta minus theta can be written as theta minus 1 times a polynomial with degree 2. It's very easy to find the polynomial with degree 2 by just solving a little system. And then again, you can find the roots of this polynomial with degree 2, and that again gives you theta infinity. Okay? So degree 2, that's easy. Degree 3, you can use this trick that theta equals 1 is always a root, and then simplify your polynomial, decrease the degree by 1, and you can again find the roots. Okay. Then of course things become more complicated if many of those pKs are strictly positive. So there are special cases where all the pKs are strictly positive, and we can still find exactly theta infinity. So the most popular example is where the offspring distribution is a shifted geometric random variable, in which case all the pKs are positive, but then you can write explicitly this infinite sum, and you can find the zeros of this sum, and then you again get theta infinity. But for a very general offspring distribution, okay, where many of the pKs are strictly positive, it's possible that you cannot find the solution. In fact, you have a very popular result, a very important result from Galois theory that tells you that polynomial with degree 5 or above might not be solvable by radicals, which means that even if the roots exist there somewhere, okay, it's not possible to express the roots using the coefficients of your polynomial and basic operation like square root, cubic root, and so on. Okay? And so, again, it's possible if too many of your pKs are strictly positive, this function is too complicated. In this case, you cannot find explicitly the expression of theta infinity. But you can always use a computer to plot this function, and then your computer is going to give you a good approximation of theta infinity, from which you can deduce the probability of survival. Okay? It's always better than running a bunch of simulation of the process to try to have an estimate of that. That's not going to be very precise, while using a computer to directly plot this function and find the fixed point from the computer, that's going to give you a better approximation for the value of theta infinity. All right. So I'm done here, but I'm done with all the theory, but let's go back to give you an illustration. Let's go back to the example I already showed you before. Okay? I showed you those simulation pictures at the beginning of this video, okay? Telling you that these are sample paths of the Galton-Watson branching process with this offspring distribution. Individual, they have 0 offspring with probability 0.2, 1 offspring with probability 0.5, 2 offspring with probability 0.3. And I told you at the beginning of this video that at the end of this video, looking at those numbers, we should be able to easily, looking at those numbers, say that we are in the supercritical phase. This process should survive with positive probability, and even better, we can compute actually the probability of survival, like explicitly. So, how does it work? Well, just look at from that you can easily look at the value of mu. In this case, the mean, the expected number of offspring per individual, is just equal to 0 times 0.2 plus 1 times 0.5 plus 2 times 0.3. That's 0.5 plus 0.6, that's 1.1. That's indeed strictly larger than 1. So we are indeed in the supercritical phase. You see that just this little calculation that tells you that the probability of survival is strictly positive. Now, how do we compute actually the probability of survival in this case? Well, we need to find the fixed point of the probability generating function. The probability generating function is equal in this case to 0.2 plus 0.5 times theta plus 0.3 times theta squared. And we want to see when this is equal to theta. Okay? So if you move your theta on the other side, the goal is basically to find the roots of the polynomial 0.2 plus 0.5 minus 1, that gives you a minus 0.5 times theta, plus 0.3 theta square equals 0. You want to solve that, okay? And then eventually you can easily see that, okay, this polynomial, you can just simplify it, like multiply it by 10, and so you get, the goal is to find the roots of the polynomial 3 theta square minus 5 theta plus 2, and so we want to solve this equals 0, but again, theta equals 1 is always a root, and so you can express this as theta minus 1 times a polynomial with degree 1. You can easily see that this polynomial is 3 theta minus 2, okay? So that gives you two fixed points, okay? Exactly like in the picture before, in the previous slide. First fixed point that is always a fixed point is theta equals 1. The other fixed point is theta equals 2/3, okay? You need to take theta equals 2/3 to make this equal to 0. Okay, so theta equals 2/3 is your theta infinity probability of extinction, and so you deduce that in this particular case, the probability of survival is 1 minus your probability of extinction, so 1 minus 2/3, and so conclusion, in this specific case, you can prove that the probability of survival is equal to 1/3. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 7 of my stochastic modeling book. That's the chapter about discrete time Markov chain, which is one of the most popular topics in the field of stochastic processes.